Hello everyone and welcome back to the Statistics video lecture series. Today we are going to be calculating what are called measures of variation. So a measure of variation is also known as a measure of spread, and there are multiple ways to measure variation or spread. So a measure of variation are measurements of how spread out is this data set. Are all of the data entries mostly clustered together around one particular value, such as the mean? Or is the data really spread out with entries all over the spectrum and all over the place? So there are a bunch of different ways to measure variation, and the most simple one that you've probably learned before is called the range. The range is the difference between the maximum and the minimum data entries in a data set. It's really easy to calculate. It's just a simple subtraction. But the problem with range is that it only contains information about the maximum and the minimum values. It tells you how far apart are the minimum and the maximum. It tells you absolutely nothing about the values in between. It tells you nothing about the variation or spread of the data values in between those two. It just tells you about the maximum and the minimum. So what we're going to do is we have here the starting salaries in thousands of dollars for a particular corporation, and we're going to find the range of this data set. So for the range, it is simply going to be the maximum data entry minus the minimum data entry. So the maximum data entry is 47. The minimum or smallest data entry is here at 37. So this range, you just simply subtract them and you get 10. So what that means is that this data has a range of $10,000, which means that the maximum and the minimum data entries are $10,000 apart. Now, deviation is another measure of spread. So the deviation of a particular data entry X in a population data set is the difference between that data entry and the population mean mu of the data set. So in other words, deviation is how far a singular data entry deviates from the mean. How far away is this particular data entry away from the mean? And deviation also measures whether that value is greater than the mean or less than the mean. So the deviation for a particular data entry X is given by the formula X minus mu. X, the data entry X minus the population mean. And it is always in that order. You can have a negative deviation, and we're going to talk about what that means. So what we're going to do is we're going to calculate the mean of this data set here for corporation A, and then we're going to use it to find the deviation for the data entry 41 and the deviation for the data entry 45. So if you were to add all of these together and divide by how many there are, you get a you get a population mean of 41.5. So if the mean is 41.5, what we're going to do is we're going to calculate the deviation for the data entry 41. So the deviation for 41 is going to be the data entry itself, 41, minus the mean, 41.5. And then 41 minus 41.5 is negative 0.5. And we're going to talk about what this means in just a second. But what I want you guys to do is just really quick. I want you guys to pause the video and calculate the deviation for the data entry 45. All right, so the deviation for 45 is going to be the data entry itself, 45, minus the mean, which was 41.5, and then that will give us a deviation of 3.5. So these deviations, the deviation for 41 was negative. Remember, the average here was $41.5 thousand. So the average for that data set was 41.5. The data entry 41, it is pretty close to the mean. In fact, it is $0.5 thousand less than the mean. So 41 had a really small deviation. this deviation was less than 1. The smaller the deviation, the closer the data entry is to the mean. And since 41 is really close to the mean, its deviation was a really small number. Now, if a deviation is negative, that indicates that the data entry in question is less than the mean. 41 is less than the average 41.5. So that's why its deviation came out negative. On the flip side, the larger the deviation, the further away the data entry is away from the mean. And if the deviation is positive, that indicates that the data entry is greater than the mean. So this 3.5, which was the deviation for 45, this indicates that 45 was above the mean, which it is. 45 is greater than 41.5. And since 3.5 is fairly large, this indicates that 45 is $3.5 thousand above the mean. Now, that is really handy. The issue is that deviation is only measured for each individual data entry. Each individual data entry will have its own deviation, and the deviation is going to be different for each data entry. And while that's handy, that doesn't really tell you a whole lot about the spread overall for the overall data. So in a lot of cases, it's handy to know the average deviation of a data set. It's handy to know, okay, what's the deviation for these data entries on average? On average, how spread out are these values? On average, what do their deviations look like? The problem is you can't just take an average of the deviations, because in any data set, the sum of all deviations is 0. So since the sum of all the deviations is 0, you can't just simply add them all up and divide by how many there are like a typical mean. So what we do instead to measure, okay, how spread out on average is this data set? What's the deviation on average? We're going to square all of the deviations, add them all together, and divide by capital N, which is the size of the population. When you square all of the deviations, add them up, and divide by population size, you get what is called population variance. So the population variance is given by this formula, and I'm going to walk you through each part. Remember that you need to do order of operations whenever you're doing any sort of formula. Parentheses go first. So in the parentheses, we have x minus the population mean. This means that you are finding each individual deviation. After parentheses come exponents, so you will square each of those deviations. Then, based on the way this formula is set up, you will need to then add them all together. And then after you add them all together, you are going to divide by capital N, the population size. Now, this symbol right here, this is the Greek letter sigma in lowercase. So this is sigma in uppercase, this is sigma in lowercase. So sigma squared is the population variance. And that's the symbol we use for population variance. Now, one problem with variance is that the units for variance don't match up with the units of the original data, because while deviation itself is in the same units as the original data, when you square it, you're going to get squared units. So for example, the variance for the salary data set would be in thousands of dollars squared instead of thousands of dollars. Dollars squared is not really useful. So that's why variation, while it is calculated, isn't used all that much, and it's really a means to another end. So to make the units match, we're going to undo that squaring by taking what is called a square root. So to make the units match, we're going to take the square root of variance, which is called standard deviation. Standard deviation is one of the most important statistics to compute because it's got a lot of uses. What standard deviation is going to be for us for now? It is going to be a measure of average spread. Standard deviation is going to tell us how spread out on average are the entries in this data set. What is the deviation for these data entries on average? What's the average deviation? Now, I will say that we are not going to be calculating standard deviation by hand. I am going to show you calculator steps in just a bit. But if you do not have a graphing calculator, you will have to do this formula by yourself. Now, standard deviation is simply the square root of variance. So we have population standard deviation, which is denoted by the Greek letter sigma, lowercase sigma. And it is simply the square root of variance. So this is the variance formula with the square root. So if you're calculating standard deviation by hand, you would need to calculate each individual deviation for each individual data entry, x minus the mean, then square them all, then add them all together, then divide by the population size, and then at the end, you're going to take the square root. Now, standard deviation is a measure of spread. Standard deviation measures how spread out away from the mean are the data entries. How far away is a typical data entry away from the mean? How far away is a typical randomly selected data entry away from the average? So the standard units has the same standard deviation has the same units as the original data. So the standard deviation for the salary data set would be in thousands of dollars, just like the original data. Now, standard deviation, because the square root can only ever give you a positive number, standard deviation is always some positive number greater than or equal to 0. When the standard deviation is exactly equal to 0, that means the data has no variation at all, and all of the data entries have the same value, which would be the mean. Now, the bigger the value of sigma, the more spread out the data set. So the higher the standard deviation, the more spread out the data set, because a higher standard deviation will indicate that on average, the deviations for these data entries are higher. Now, on the flip side, the smaller the standard deviation, the more clustered together the data entries. So the smaller the deviation, the standard deviation, the less spread out the data set. Now, as entries get farther and farther from the mean, deviation is going to increase. So that's why the bigger the standard deviation, the more spread out the data. Now, that was for population. So we have population variance and population standard deviation. Population variance had the variable sigma squared. Population standard deviation had the variable sigma. Since populations and samples are different, not only do sample variance and sample standard deviation have different formulas, they also have different variables to represent them. So sample variance is going to be denoted as s squared. And it is going to be the same idea, x minus the sample means, all of them squared, added together, and divided by sample size, minus 1 this time. Now, sample standard deviation, which is going to be denoted by the variable s, is just the square root of that sample variance formula. Again, don't agonize too much over this formula. If you do have the course required graphing calculator, I am going to show you how to calculate sample standard deviation on a graphing calculator. So sample standard deviation, I am not going to expect you to calculate by hand. You can use a graphing calculator to calculate this. Now, these are the steps to find the standard deviation and other statistics on a TI-83 or TI-84. Unfortunately, the computer that I'm using to record this is really not great, and its processing power is terrible. So I will assure you that if I try to show you the calculator steps in the same video, I'm going to crash the PC. So I've gone ahead and pre-recorded the steps on how to find standard deviation and a whole ton of other statistics on a graphing calculator, and I'm going to leave a link to that video in the description. But in general, we are going to be using the one-var stats feature on the graphing calculator, and not only is it going to calculate sample standard deviation, it's going to calculate a whole bunch of other statistics as well, such as sample mean. It will also calculate what are called the quartiles, which we're going to get to in the next video, and minimum and maximum, so it's got a whole bunch. Now, for these purposes, SX is the symbol on the calculator that indicates the sample standard deviation. So when you're using a calculator to find sample standard deviation, you're going to look where it says SX. Now, if you need to find the sample variance, all you have to do is take whatever value it gave you for SX and square it. So if you need to find the variance, just square the standard deviation it gave you. Now, this is a very large menu, and as you'll see in the other video, you can scroll through it, and there's a whole bunch of other statistics, a lot of which you'll recognize, and a lot of which we're going to also be using in the next video. So I do this exact example in that other video. I'm going to leave a link to it in the description. Now, a little bit more about standard deviation. Standard deviation itself can also be a unit of measurement. So number of standard deviations is a unit of measurement of how far away from the mean a single particular data entry is going to lie. So for example, let's say that you have a data entry that is 2.5 standard deviations away from the mean, to the right of the mean. That is going to be a lot greater than, let's say, a data entry that is only 1.3 standard deviations to the right of the mean. So standard deviation itself can also be a unit of measurement of how far a particular data entry deviates away from the mean. So it can tell you, okay, something that's 2.5 standard deviations away is a lot farther than something that's, let's say, 1.3 standard deviations away. Now, any data entry that is 3 standard deviations to the left or right of the mean is considered very far away from the mean. When you have a data entry that is this far from the mean, these are extremely unusual values. And any data entry that is more than 3 standard deviations either to the left or to the right of the mean is extremely unusual. Now, on the flip side, a data entry that's, let's say, 0.2 standard deviations away from the mean is very close to the average. So if you, let's say, have a data entry that is less than 1 standard deviation from the mean, we can say that it is pretty close to the mean. The mean itself is 0 standard deviations away from the mean. So remember that standard deviation is a measurement of the typical amount of spread, a typical amount that a data entry deviates away from the mean. The more the entries are spread out, the greater the value of the standard deviation. If your standard deviation is 0, like in this first graph here, that means that all of the data entries are the exact same and they are all equal to the mean. So this is an example where the mean is equal to 5, but with a standard deviation of 0, that means all 8 of these values all have the same value, 5. In the second graph here, we have another sample mean of 5, but this time the standard deviation is 1.2. So a standard deviation of 1.2, there is a little bit of spread. You can see that the mean itself has the highest frequency, so most of the values are at the mean. The second highest frequencies are just right around the mean itself, just a little bit to the left and a little bit to the right. Not as many, but you have some that are to the left and right and pretty close. And the further away that you get from the mean, the fewer data entries there are. So there's only 1 here at 3 and only 1 here at 7, and there's nothing past that. Now, the greater the standard deviation, the more spread out the data. So this third graph is an example where the sample mean does come out to 5. But if you take a look at the standard deviation, we have a standard deviation of 3. A standard deviation that high indicates that the data is really spread out. And if you notice, there's absolutely no data entries here at 5. The data entries that were there just happened to average out to 5, even though we have no data here at 5. But take a look at the frequency distributions. The highest frequencies are over here at 2 and 8, which is very far from the mean. We have a couple at 3 and 7, and then nothing as we get closer to 5. So a standard deviation this high indicates a really spread data set, and you can see that this data set is really spread out. Now, if you were to, let's say, draw a curve around this second distribution here, it would look something like this. This type of curve right here is a very special curve that you may have heard called a bell curve before. So a bell-shaped distribution, which is called a normal curve, and we're going to actually look at these a lot later in Chapter 5. But what a bell-shaped distribution is it is a distribution that is symmetric and bell-shaped, and that is extremely important. Not all distributions, as you can see, form one of these shapes, but there are some distributions that do. So when you do have a distribution that is symmetric and bell-shaped, what that means is that most data entries are all clustered around the mean, with very few entries that are either far above or far below the mean. Like in this second graph here, most of the data entries were at or around the mean, with very few, if any, as you go further out. Now, there are some populations in the real world that just follow a bell curve, and we know it. Like, for example, men and women's heights, they follow a bell curve. There's just a couple of those distributions we know for a fact do. There are other distributions that may or may not follow one of these bell curves, and some sample distributions may or may not follow one of these. We're going to talk a lot more extensively about those later. You may have also heard of bell curves used in the context of class grades. So let's say that grades on a test follow a bell curve. What that will mean is that most of the grades are all clustered around the average, probably a C, with very few entries that are either far above the mean, like in the A+ range, or very far below the mean in the F range. So if grades follow a bell curve, most of the grades are right around the average, with fewer and fewer grades as you get further and further away from the class average. Now, if you do have a data set that has a distribution that is symmetric and bell-shaped, you will know a certain percentage of the data will lie within given standard deviations of the mean. So if you do have a distribution that is symmetric and bell-shaped, what that means is about 68% of the data is going to lie within one standard deviation of the mean, either to the left or to the right. And what I have here is a drawing to illustrate that. So here is a bell curve. It is symmetric and bell-shaped. And right in the middle, right at the highest point, is the mean. So if you have a data entry that is either one standard deviation less than the mean or one standard deviation greater than the mean, 68% of the data is going to fall within one standard deviation of the mean. About 95% of the data is going to lie within two standard deviations to the mean. So between two standard deviations above the mean and two standard deviations below the mean, so between there and there, approximately 95% of the data falls between there and there. So 95% of the data is going to fall between two standard deviations of the mean. Then approximately 99.7% of the data is going to fall within three standard deviations of the mean. So between three standard deviations above the mean and three standard deviations below the mean, so from there to there is 99.7% of the data. Not quite 100, because you can have data entries that are greater than three standard deviations away. These are extremely unusual, but since it can happen, it's not quite 100% of the data. But approximately 99.7% of the data will fall within three standard deviations of the mean. And this is something called the empirical rule, and the empirical rule you will need to know. You will have homework and exam questions on it. This will give you a certain percentage of the data on a symmetric and bell-shaped curve will fall between certain standard deviations of the mean. Now keep in mind, this 68%, for example, is between one standard deviation less and one standard deviation greater. Since this is symmetric, if you have 68% is between here and here, that means on either side of the mean, from the mean to one standard deviation above is 34%, and from the mean to one standard deviation below is another 34%. Also, from the mean to, let's say, two standard deviations below is going to be 47.5%, which is half of 95. And then another 47.5% will lie between the mean and two standard deviations above. So keep in mind that since it is symmetric around the mean. And since it's symmetric around the mean, that means that the right half of this bell curve is a perfect mirror image of the left half of this bell curve. So let's say that in a survey conducted, the sample mean height of women in the United States in the age range 20 to 29 was 64.2 inches. So they just gave us that the sample mean of the survey they took was 64.2. And the sample standard deviation for that sample was calculated to be 2.9 inches. So S equals 2.9. I write my S's in cursive because they look a lot like 5s. And what we're going to do is we are going to estimate the percent of women whose heights are between 58.4 inches and 64.2 inches. And men's and women's heights are going to follow a bell curve. And if you're, populations like that we know follow bell curves. In other populations that don't always follow bell curves, if it tells you that the distribution is symmetric and bell-shaped, you can use the empirical rule to estimate these percentages. So what I'm going to do first is, before I get into any of the percentages, I'm going to draw the bell curve for this as best as I can with this terrible stylus. So pretend that's a symmetric and bell-shaped curve. And right in the middle, we're going to have our sample mean. So our sample mean is going to be right here in the middle at 64.2. Now remember, the standard deviation is 2.9 inches. So a woman who has a height of exactly 64.2 inches is going to be exactly equal to the mean. Now, one standard deviation above the mean would be 64.2 plus 2.9, which gives us 67.1. So a woman that is 67.1 inches tall will be exactly one standard deviation above average. Now, two standard deviations above the mean would be 67.1 plus 2.9, which gives you 70. So a woman who is 70 inches tall will be 2 standard deviations above the mean. And then 3 standard deviations above the mean would be a woman who is 72.9 inches tall. So this is getting very far above the mean. 72.9 inches is a lot greater than 64.2 inches. So we're getting more and more unusual, and we're getting less and less data, as demonstrated by the fact that the curve is getting closer to the x-axis here. So a woman who is 72.9 inches tall would be 3 standard deviations above average. Now on the flip side, if you have 1 standard deviation below the mean, that would be 64.2 minus 2.9, which is 61.3. So a woman who is 61.3 inches tall would be 1 standard deviation below average. Then 2 standard deviations below the mean would be minus another 2.9, gives us 58.4. So a woman who is 58.4 inches tall would be 2 standard deviations below average. And then 3 standard deviations below the mean would be subtract another 2.9, and we get 55.5. So a woman who is 55.5 inches tall in this sample would be 3 standard deviations below average. And again, this is getting more and more unusual. The curve getting closer to the x-axis indicates that we have less data, so we're getting farther and farther away from the mean. Now, the empirical rule says that 68% of the data is going to fall within 1 standard deviation of the mean. So that means 68% of women are going to have a height between 61.3 inches and 67.1 inches. Empirical rule also says that 95% of the data is going to lie within 2 standard deviations of the mean. So between 2 standard deviations, that is between there and there, is 95% of the data. So that means that 95% of the women in this sample had a height between 58.4 inches and 70 inches. And then 99.7% of the data is going to lie within 3 standard deviations of the mean. So from here to here is going to be 99.7% of the data. So 99.7% of the women in this sample had a height between 55.5 inches and 72.9 inches. So that is what the empirical rule looks like. Now, to actually answer the question, we're estimating the percent of women whose heights are between 58.4 inches and 64.2 inches. And I'm actually going to change color for this. So here's that 58.4. That is 2 standard deviations below the mean. And here's 64.2, which is exactly equal to the mean. Let me try that again. There we go. Now, 58.4 was 2 standard deviations below average. This 95% here only applies between 58.4 and 70. That's not exactly what we're looking for. We're looking for the percent of women that are between 58.4 and 64.2. Now, since 64.2 is exactly equal to the average, remember this data is symmetric around the mean. So since the curve is symmetric around the mean, that means that from here to here is half of 95%. This is half of that section between 2 standard deviations. So half of 95 is 47.5. So that means 47.5% of these women have heights between 58.4 inches and 64.2 inches. So that would be 47.5%. And then on the flip side, on the other side, would be another 47.5%. All right, so that is it for now for standard deviation and for the empirical rule. We are going to be covering symmetric and bell-shaped distributions a lot more extensively later in the course, so do be prepared to see those again. This is just kind of an introduction to those type of distributions. So thank you all very much for watching. In the next video, we're going to be covering measures of position, which measure a data entry's position in a data set in relation to the other data entries. So stay tuned for that. Thank you all very much for watching, and I will see you in the next video. Bye-bye.